Is there anybody that doesn't have permission for being on like Twitter and Facebook and?
We signed a thing last year.
Are you?
A waiver.
There should have been a waiver signed this year. Is there anybody that doesn't have permission for stuff like that? Because I'm going to upload this to YouTube. You can upload it and make it a private link, can't you? You're not recording now, are you?
Yeah.
Right then, stop recording. Now, wait. You're not filming me, are you?
Yes, I am.
Film this! Are you just going to edit this down? So it's a piece of metal, and down the bottom here we just have a piece of gold leaf, which is just fixed here. So if I charge this piece of metal up here, all of this will become the same charge, and the piece of gold foil will lift up. So what we're going to do is we're going to shine some light onto this. So there's some light going on and nothing happens. Awesome. What we're going to do now, and what possessed somebody to do this experiment I don't know, but it's very cool. They're going to put a piece of zinc on the top. And it has to be a clean piece of zinc. So we clean it off so that there's no corrosion, so that all the light that actually gets to it will hit the zinc and will interact with the zinc, not the corroded layer. So now we're going to shine some light on it. Let's shine green light. It does nothing. Let's change the lights. Let's make the light blue. It does nothing. What we're going to do now is we're going to change it to ultraviolet light. So when we shine ultraviolet light, all of a sudden, electrons start leaving the piece of zinc, which makes the zinc positive. So because the zinc is positive, electrons then from this piece of metal come up to replace the electrons that are coming off, making this part positive. The same happens all the way down, and everything becomes positive, so therefore the piece of gold foil now repels because it's all positive. So what we're doing is we're actually making this charged using light. We're going to investigate now how much energy these electrons have. So we've got the piece of zinc here, and it's in a vacuum container. So there's no air particles to interact with any electrons that are given off. We've then got a potentiometer, so we can go anywhere between 0 volts and the maximum, which is the voltage of the supply. And this is set up opposing any electron trying to come off. So this side will become negative, this side will become positive. The idea is we're going to shine light in, and it's going to hit the zinc. When it hits the zinc, it's going to let electrons come off the surface, and they're going to have energy. And they're going to have kinetic energy. What we're going to do is we're going to take away that kinetic energy by using electric potential energy. So we're going to have a negative charge here that's going to repel this negative, and the positive voltage is going to attract it. So we'll change the voltage, the potential we've got across here, to find out how much energy we need to take away. When we fully stop the electrons, the current will be what value? Zero, because no electrons are flowing. So what we do is we do lots of different colours of light. So we have this light coming in, which actually will come as photons, but we'll find out about that later. They're going to come in, and we're going to find out what potential we need to stop electrons coming across. That's called stopping potential. So we're going to do this for lots of different coloured lights, and we're going to see how this goes. Okay, so what we're going to do is we're going to plot the energy that each electron has, the maximum energy you're getting, against the frequency of the light. And what we'll do is we'll actually get a line like this. This is not proportional because it doesn't go through the origin. So you'll see at this point, if I have a frequency less than this, I get no energy of electrons. So no energy is given to electrons. There's no electron being released. So that is called, pause, that's the threshold frequency. That's the minimum frequency you need to release an electron from that material. So we call it F subscript T. Now what we can do is we can actually backtrack this line, we can extrapolate. And this will give us an intercept here. the gradient is always the same. And the gradient equals Planck's constant. Stop. 6.63 times 10 to the minus 34 joule seconds. And that's Planck's constant. Now, if we backtrack, there's an interesting point here as well. This point tells us the negative energy required to release an electron. So that tells us the actual energy you need to release the electron that's sitting on the surface of the substance. So at the threshold frequency, the energy supplied only gets an electron to the surface, so it's got no kinetic energy. If we go below that, then no electrons are actually released. Pause. There was something else I was about to say.
So but then what is negative 5?
I had to go on about this. Ready? 3, 2, 1. Action. Now, because it's impossible to get any electrons released below the threshold frequency, it doesn't matter how bright the light is or how long you have the light shining for, it can't happen. It means that light is not acting like a wave here. It's acting like a particle. If it acts as a wave, if you increase the intensity, the brightness of the light, you would get enough energy in one place to actually release an electron. You don't here. So the big reason why this is acting as a particle is because one photon releases one electron. The photons can't add together. You can't superimpose the photons in this. So therefore it's acting as a particle, not as a wave. So this is actually showing us wave-particle duality, because we know that light can reflect, it can refract, it can diffract like waves, but it can also act here as a particle. Okay, let's reduce this to an equation. We're going to have an electron. It's going to take a certain amount of energy to get this electron right to the surface, where it's just sitting on the surface, ready to leave. And that is called the work function. So that's how much energy you need just to get the electron just to the surface, so it's just ionized. So the energy supplied is going to equal the work function plus any extra energy is going to be released as kinetic energy. So that if you've got more energy than the work function, you're going to give it kinetic energy. And in the previous experiment, we talked about putting that in an electric field to work out how much kinetic energy there was. So we get, are you ready? Okay. If we look back at the graph, the energy here was actually the kinetic energy, and this was the frequency. So what we're going to do is the graph that we had, we're going to look at it as a y equals mx plus c. So this is y. This is going to be mx, because remember, the x is f. And earlier we said that the gradient was going to be this thing called Planck's constant. So we've now got hf equals phi, the work function, the amount of energy required to get an electron just to the surface, to just ionize it, plus the kinetic energy. Rearranging that to y equals mx plus c, you get the kinetic energy equals hf minus phi. So you see, this minus phi is the intercept on the y-axis, this part here. So that means where this intercept is, it's actually the minus the work function, which is why you can extrapolate this line back, read off the work function, change the sign, and you know how much energy it takes to ionize it. And that's the minimum amount of energy. If this electron was buried deeper inside, it would take more energy. If the surface was corroded, it would take more energy, so that would affect the work function. The kinetic energy of the electron given off is going to be a half mv squared, where the m is going to be the mass of an electron. You're also going to have the kinetic energy is going to equal the same as the electric potential energy taken away, which is the stopping voltage times by the charge of the particles, so it's times the charge of an electron. So if we know in electron volts how much energy it is, we can work out the kinetic energy straight away. So we could do the stopping voltage times by negative 1.6 times 10 to negative 19 coulombs will equal a half m as in mass of the electron, v squared. So you could rearrange that to find the velocity. Obviously, to do that, you're going to have to ignore the negative. So you can take that last bit off. Right.
What does the bottom one say?
Vs times, and then I'll just put the charge of an electron in 1.6 times 10 to the negative 19.
It does.
So what we're going to do is we're going to look at what happens to the current with the potential for ultraviolet light shining on zinc. But we're going to do it for 2 different intensities. So first of all, we're going to do it for a low intensity UV. And it does that. That's low intensity ultraviolet. Now obviously if we did this with like green light or red light, we wouldn't get any current at all. If we do this with a higher intensity, we get a graph like this. That's a high intensity UV light. Now what this tells us is if you have a more intense light, you've actually got more photons arriving. Because remember, it's 1 photon, 1 electron. So for low intensity, when we put the potential up, so every electron that gets to the surface that's given that work function is stripped off and is accelerated across the gap. So that's why up here. Down here, we've actually got negative, so therefore we're stopping some of the electrons. Here, we're having no effect, but some of them don't have enough kinetic energy to make the gap. So when we get over to this part, we're actually making sure every electron that's released goes all the way across. So that's why we get a limited current. So 1 photon, 1 electron. Low intensity gives us less electrons released, so it has less photons. High intensity gives us a bigger current, so more electrons are released off the zinc. And you can count.
For the previous graph, is it that we don't get any energy in visible light because it doesn't have enough frequency?
Yeah.
So like even if it's high intensity, if it doesn't have the right frequency,
It will do nothing because it doesn't act as a wave.